All right, what we need to do then is we need to talk about mixtures, gas mixtures in particular. When we're thinking about gas mixtures, there are four ways to visualize what a gas mixture is. One way is percent by mass. Percent by mass. Let's say you have 100 grams of mixture. How many grams of each component do you have? Let's say you have 50 grams of A, then it would be 50% A by mass. Right? And then we have percent by mole. Percent, let's say you have 100 moles, and then 50 moles of A, then would be 50% A by mole, but they typically aren't the same thing. Like, for example, water. What is the percent composition of water? If we do the percent composition of water, we could do it in two ways. We could do it percent by mass, or we could do it percent by mole or atom. Percent by mass would be, how many grams of hydrogen? Well, what does water weigh? Do you know how much water weighs? Water molecule? 1802. A single water molecule, the average water molecule weighs 18.02 U. A mole of water molecules would weigh 18.02 grams. Right? And so if I want the percent hydrogen by mass, then it's a mole of water. A mole of water weighs 18.02 grams. How much, in 1 mole of water, how many moles of hydrogen do I have? 2 moles of hydrogen. 2 moles of hydrogen weighs 2.02 grams. It's 100%. And so this is going to just give us roughly 11% hydrogen. And then the percent oxygen by mass is, we have 1 mole of oxygen for every mole of water. A mole of oxygen weighs 16.0 grams, or 18.02 grams, times 100%. This gives us 89% oxygen. So it's 11% hydrogen, 89% oxygen. That's how we say the composition of water. And so if we were to do a mass ratio, the mass ratio would be H11, O89. Are chemical formulas mass ratios? No, chemical formulas are not mass ratios. Chemical formulas are mole ratios. And so if I look at H2O and do a percent of hydrogen by mole, it's different. How many moles of hydrogen atoms do I have? I have 2 moles of hydrogen atoms. Out of a total of how many moles of atoms? 3. And so it'd be 1/3%, which would be 33% hydrogen, and percent oxygen, well, it's 2/3, so it'd be 67% oxygen. It's the same, it's the same water, but it's 2 ways of visualizing water. One way is by visualizing by mass, another way is by visualizing by mole. We're much more accustomed to visualizing it by mole than mass. And it's actually much more convenient. For gases, we have some additional ways. For gases, we have we have percent mass, percent mole, percent volume, and percent pressure. So let's look at those. This is in chapter 15, so we're going to jump up to chapter 15 for a little bit, then come back down to chapter 14. I'm going to do a simple gas mixture. I'm going to take, let's take air. Let's say this air, I'm going to keep the composition simple. I'm going to say that this air is 80% nitrogen and 20% oxygen. So that adds up to 100%. Air is more like 21%, oxygen 79% nitrogen. But that's going to be close enough. These are percent by mole. And when I do percent by mole, that means if I had 100 moles, I've got 80 moles of nitrogen, 20 moles of oxygen. If I have 100 molecules in here, then 80 of the molecules will be nitrogen. So let's do 100 molecules in this box. 80 of those molecules will be nitrogen. And then 20 of those molecules will be oxygen. That's what a mole percent is. It's a number percent based on the molecules. So 20% of the molecules will be oxygen, 80% of the molecules will be nitrogen. Now, there are two ways of visualizing this particular mixture, and they're all related. And so this is 2, 3, and 4. One way is if I have 100 liters of air, and it has this composition, how many liters of nitrogen do I have? Take a guess. How many liters of nitrogen would I have? And how many liters of oxygen would I have? 80 and 20, right? And so one way of visualizing this mixture is, I would say this mixture consists of 80 liters of nitrogen. And so I'll put all the nitrogens, nitrogen is 80% of this, so I'll have a box. It's just going to be 80% of the total nitrogen. And then I'm going to have a 20 liter box that I can put my oxygen in. So I'll have 20 liters of oxygen. And so I'll just separate it into two boxes. I'll put my nitrogen in one box. I'll need an 80 liter box for that. And I'll put my oxygen in another box. I'll need a 20 liter box for that. And then I have my mixture. This is my mixture. And so if I do 80 liters plus 20 liters, that gives me a total of 100 liters of mixture. Now, in order to characterize a gas, I need to know the volume. I need to know the pressure too. And so what is the pressure of the nitrogen here? Well, if I just remove the nitrogen out of here, it's going to be the same pressure. The pressure is not, I'm going to make it higher or lower. And so this is going to be at 1 atmosphere. So I have 1.00 atmospheres of nitrogen. It's the same pressure. And if I take out the oxygen, it's going to be at the same pressure. It's going to be 1.00 atmospheres of oxygen. However, if I do this, if I take 1 atmosphere of oxygen and 1 atmosphere of nitrogen and add them together, what do I get? So I'll take 1 atmosphere of nitrogen plus 1 atmosphere of oxygen, and I get, you would think 2 atmospheres, but you know what we get? We get 1 atmosphere of mixture. Because what we're going to do is we're just going to put these side by side. We aren't compressing it, we aren't expanding it. We're just going to take them side by side. We get 1.0 atmospheres of mixture. In other words, the atmospheres of nitrogen is equal to the atmospheres of oxygen, which is equal to the atmospheres of mixture. Keeping everything level. This is called Avogadro's law. And that is the volume of nitrogen plus the volume of oxygen is equal to the volume total, or the volume of mixture. And so, in other words, this is 80% by volume nitrogen. And it's 20% oxygen by volume. So it's the same, you know, it's 80% nitrogen by mole, 20% oxygen by mole. It's 80% nitrogen by volume, 20% oxygen by volume. And when the pressures are equal like this, we call it constant pressure. Constant pressure. That is, the pressure doesn't change. We don't want it to get high or low. This is Avogadro's. There's another way of visualizing this mixture. This other way of visualizing the mixture we call Dalton's. What Dalton does is that he doesn't divide it like this. If I have 100 liters of air at one atmosphere of air, the way I'm going to separate it is into two equal sized boxes. I'm going to get 100 liters of nitrogen. And so I'm just going to remove the oxygen out of here. Now, pressure is caused by the collisions of the gas particles with the wall. So if I remove all the red particles out of here, I'm going to have fewer collisions, and therefore I should have lower pressure. And so if I have 100 liters of nitrogen here, and there's no more oxygen in this box, then what is the pressure? Do you know what the pressure is? Take a guess. It's not 1 anymore, it's 0.80 atmospheres of nitrogen. It's 80% of the pressure because we're missing 20% of the collisions. 20% of the collisions were caused by oxygen. Now we don't have those, so we only have 80% of the pressure. Plus, I'm going to make another 100-liter box. And in this 100-liter box, we're just going to put the oxygen. So I'm going to have 100 liters of oxygen. If I have 100 liters of oxygen, what must the pressure be? Well, I'm putting all those oxygens, and all I'm doing is I'm getting rid of all the nitrogen. So I've just lost 80% of my collisions. That means the pressure of the oxygen is going to be just 20% of the total, which is 0.20 atmospheres. So this is what happens. 0.80 atmospheres plus 0.20 atmospheres is going to give me 1.00 atmospheres of mix. Sure. However, what 100 liters plus 100 liters gives me what? 100 liters plus 100 liters should give me 200 liters, but in this case, what am I doing? I'm taking 100 liters and 100 liters and just putting them into one 100-liter container. So 100 liters plus 100 liters gives me 100 liters of mix. In other words, the pressure is constant. And so in this case, the pressure of the nitrogen plus the pressure of the oxygen is equal to the total pressure. And the volume is constant. Everything has 100 liters, or everything has the same volume. This is Dalton's. Avogadro's and Dalton's cannot be simultaneously true. It's one or the other. Either everything has a pressure of 1 atmosphere in this case, and then the volumes will differ, or everything has a volume of 100 liters and the pressure is different. And so this is going to be 80% nitrogen by pressure by atmosphere. So by pressure, and 20% oxygen by pressure. So there are two ways of answering this. Let's say I had 100 liters of air at 100 atmospheres. 100 liters of air at 100 atmospheres. How much nitrogen do I have? I'd have 80, what? Atmospheres or 80 liters? Or both, 80 atmospheres and 80 liters. So let's try a little example here. We know that air is going to be about 80% nitrogen. And so if I have 100 liters of air at 100 atmospheres, how much nitrogen do I have? 80 atmospheres? Okay. I'd have 80 atmospheres in how many liters? 100 liters. So I would have 100 liters of nitrogen. If I have 100 liters of air, 100 liters of air consists of 100 liters of nitrogen, but at 80 atmospheres. And so I'll let the nitrogen, this is it, 100 liters of nitrogen at 80 atmospheres. And that's what it is, because the nitrogen is free to go anywhere in this 100 liters. Or one could visualize this. Alternatively, we could say that we have Alternatively, we could say that we have 80 liters of nitrogen. So if I have 100 liters of air, I would have 80 liters of nitrogen at a pressure of 100 atmospheres. So those are the two ways of thinking about it. Okay, so let's go back to this problem here. Let's see how we want to describe this one problem. So the first thing is I'm going to produce the nitrous oxide. So I have ammonium nitrate, solid that's going to decompose into nitrous oxide, gas, plus 2 gaseous waters. And so what I have is I have a mixture of nitrous oxide and water. But not just in any ratio that we want. It's going to be in a fixed ratio. What is the ratio? 1 to 2, the stoichiometric ratio. So 1 part nitrous oxide, 2 parts of water. Is that by mass? So is it by mass? Like for every 1 gram of nitrous oxide, I get 2 grams of water? No, it's not by mass, it's by mole. That's because chemical formulas and chemical equations tell us the mole ratio, not the mass ratio. If the chemical equations were mass ratios, it'd be a nightmare. All right, so what this is I have 3 moles total. And so in other words, I have 33.3% nitrous oxide, 66.7% water by mole. Now, what do I have here? I know that this is, what is this? This is 82.3 liters. And the pressure of this mixture is 896 torr. So what are the 2 ways I can describe this mixture? Well, I can use Avogadro's or I could use Dalton's. So go ahead and figure it out. Which one do you want to do? It doesn't matter. But we have to pick one or the other. We have to pick one or the other because I need to know how many, for example, I need to know how many liters of nitrous oxide I have at what pressure? Because in order to get the moles of nitrous oxide, I need the pressure, the volume, and the temperature. Now, the temperature is given here. Temperature for both gases will be 447 degrees C. So how much nitrous do I have? All right, why don't you figure out how much nitrous I have and then tell me.